where one of the systems is a neutron star. And then she moved back to Europe in 2020 in the group of Roberto, where again the focus is on massive black hole binaries. So I will then let you give your talk, and we are very happy to have you here.
Thank you so much, Lucio, for the kind introduction, and thank you for the invitation. Thank you also for showing up. So yeah, I'm going to be talking about the interaction between a binary and its circumbinary disk. So massive binary black holes can form through galaxy mergers. When two galaxies merge, they bring together, each of them brings together the whole environment that she has. So stars, gas, planets, everything. And then this material, through galaxy collisions, will sink down to the central part of the newly forming galaxy together with the newly formed massive black hole pair. Understanding the interaction between a binary and its gaseous environment is crucial because at sub-parsec scale, the binary is still too wide for gravitational waves to take over and drive the binary to merge. So this is a schematic view of the path to coalescence for a massive black hole binary. So after a successful dynamical friction-driven stage, the binary then experiences interactions with the stellar environment and gaseous environment before being completely gravitational wave driven. So below, let's say 10 to the -3 parsecs, everything is governed by gravitational wave emission. And so we just have the binary that merge. So I'm gonna be focusing on the effect of gas. So we're talking about sub-parsec scales, but I will also mention the interaction with stars at the end of my talk. Okay, so the gas that is brought together the galaxy merger will sink down to the central part, and it will, thanks to the angular momentum conservation, form an accretion disk around the binary. So basically the important additional piece of physics of circumbinary disk compared to like standard accretion disk around single objects is the presence of resonances. In particular, the co-rotation, but also more importantly, the outer and inner Lindblad resonances, which are basically thought to be the only mean through which the disk can extract angular momentum from the binary, and so will and let basically semi-major axis decrease with time. So here we have like a very, I would say, well, it's very old plot showing the radius of the resonances of these resonances that remove angular momentum. And this is basically, this was proven to be roughly correct through very early numerical simulation by Artimovic and Lubo in the 90s. The magnitude of these resonances depend on the mass ratio of the binary and its eccentricity. The binary orbit, even if it starts circular, can become eccentric as a result of this interaction. And also, the circumbinary disk has always been thought of being more a decretion disk, meaning that there is no accretion onto the binary, but it just removes angular momentum from the binary. However, these very early simulations show that there can be inflow of gas from the circumbinary edge onto the binary. But the main result of all these works was that the binary semi-major axis decreases as a function of time, decreases in time as a result of this interaction. So this is the standard picture. This picture was recently challenged by 2D hydro simulation. We're talking about pure hydro simulation, so no MHD, no GR. So this is an example of them. This is a paper by Munoz in 2019, showing the results with 2D moving mesh code Arepo. They fixed the binary orbit and they considered geometrically thick disk. So we are talking about H over R of 0.1, with H being the thickness of the disk. And they find, well, these are very noisy plots and probably also a bit out of focus, sorry. But so this is the accretion rate onto the binary. This is the spin contribution, which is basically negligible. This is the total torque. And basically the average of the total torque onto the binary is positive. This essentially means that the binary semi-major axis, if it would be allowed to evolve, it would just increase with time. So we should get binary expansion instead of shrinking. And this is not like, this is recognized in the planet community as not a terrible problem, but for binary black holes, then this might be an issue. More recently, well, a couple of years ago now, other 2D simulations with, again, fixed orbit and purely hydro have shown that actually the total torque, the sign of the total torque depends on the aspect ratio of the disk. So how cold or hot the gas disk is. So from this plot, you can see that, so this is, again, the total torque essentially, or let's say the variation of the angular momentum of the binary as a function of Mach number, which is the inverse of h/r. So towards the left side, you have thicker disks, and towards the right side, you have much colder disks. And you can see that there is a transition at around Mach number 25, which means h/r 1.04, where the torque changes sign. So it's positive before that, and it just becomes negative, like below this value. This was kind of confirmed, but not really with 3D SPH simulations of live binaries. So this time the binary is allowed to exchange angular momentum and to evolve. And the threshold for binary expansion was found to be much hotter disks. So we're talking about h/r of 0.2, which is really thick. So basically, what the two contributions of to the angular momentum evolution of the binary are the gravitational torque exerted by the disk particles onto each black hole, and the accretion of mass and the angular momentum. So you can simply write the angular momentum conservation equation, where L is the angular momentum of the binary, Tg is the gravitational torque, and Lac is the accretion contribution. You can bring this, you can decompose these in several terms, and the accretion of angular momentum is positive. The contribution of the gravitational torque is negative in the circumbinary disk, but is positive inside the cavity. And then you have the mass accretion terms, which are negative, so contribute to the shrinking of the binary. And you have an eccentricity term, which for circular binaries is mostly negligible. So this basically shows that the distribution of the gravitational torque in these systems. So you have the circumbinary disk, and you can see that, so the two binary components are the two white dots at the center. And you can see that the magenta region are the region with negative torque, and the green region are the region with positive torque. And you can see that the material, so the binary is spinning counterclockwise. So the material ahead of the black holes exerts a positive torque, while the material behind exerts a negative torque. And this is just the profile, so the torque as a function of radius. So you can see that in the circumbinary disk, which starts from 2 times the binary separation outwards, is negative, or where it's very small, but it's negative. Then you have the streams, which are the two streams of material that leak from the circumbinary disk and form the mini disk that contributes with a negative term. And then you have the so-called mini disks, or as I like to call them, circumstellar disks, which exert a strong positive torque on the sinks. The problem while investigating this system, it has been argued that with 3D SPH codes, you don't have enough resolution inside the cavity to actually to properly resolve the torques and to get the right answer. So what we did was to try and solve this problem with Gizmo, which is a multi-parallel hydro code. It has several methods of solution of the hydro equation implemented. In particular, we use the meshless finite mass approach, which is a Lagrangian approach, meaning that it conserves exactly all the quantities. And we use this with the particle splitting to be able to resolve the mini disks around the binary components. So this is just a few snapshots of our binary embedded in the disk. The two circles, one is the binary orbit and the other one is the location, the initial location of the cavity edge. So this is just to mention how this splitting technique works. So you have a parent particle that is tagged for splitting according to some criteria that you can define, and we define in the code. And it's split into two particles, each one with half of the mass of the parent. And the two particles inherit all the properties of the parent particle. And they are placed like in a random direction around the particle according to that criterion that can be adjusted, can be changed in the code. And we use this refinement within 4A, so a little bit outside of the cavity, just to make sure that we didn't influence the dynamics inside the cavity too much with this splitting. We tested the angular momentum conservation of this approach, and it's almost perfect. So here you see the cumulative change of the angular momentum of the binary in red. And then you can see that the thick black line, which is the sum of the gravitational and accretion contribution, is basically almost perfectly consistent with the binary angular momentum. This means that we are conserving angular momentum even with the particle splitting, which is not trivial because the splitting technique introduces some noise, let's say. So I mean, we started just checking that and making sure that everything was working. And then we explore the effect of the gas temperature on the evolution of the binary. So here you can see 3 snapshots of 3 simulations. One with H over R of 0.03, which should be, and it is well in the regime where you expect the binary to shrink as a result of this interaction. H over R of 0.1, which is basically the most investigated among previous work, and H over R of 0.2, which is the very thick disk that was thought to be driving the expansion. The one below is just a simple equation of state that we used. So basically, this equation of state allows the gas to be, the gas temperature to be governed by the binary in the circumbinary disk and governed by each single black hole around each single black hole. As you can see, the gas dynamics is very different comparing 3 different aspect ratio. This is the semi-major axis evolution computed directly from the simulation. So we have live binaries, they evolve, and we just track their evolution. So you can see that with very cold disks, the semi-major axis just decreases with time, which is perfect. We are in perfect agreement with all previous 3D, 2D, SPH grid-based works. With H over R of 0.1, it seems that the binary shrinks initially, but then it undergoes a very long phase of expansion, and this is the most tricky case. While for H over R of 0.2, surprisingly, we saw that the semi-major axis was just decreasing with time. So the reason for this is that if the aspect ratio is that large, there is a large amount of material that is able to enter the cavity. So the cavity remains very symmetric. And so basically the gravitational torque is very, very small just because everything is so symmetric. The gravitational torque is basically non-zero every time there is an asymmetry in the system. And the reason why the binary shrinks is that because it accretes a lot of mass and the mass accretion term is negative. The H over R of 0.1 case, which is the most studied in the literature, and it has been found to drive expansion in 2D grid codes, is very tricky to understand, and we are still in the process of finding out why there is this sweet spot for binary expansion.
So
yes.
Using the sync path.
Yes, that's correct. Yes.
Also,
yeah.
This criteria of h by r equal to 0.1, how much it depends on the mass of black hole, or like how general this criteria is for the.
You mean how general it is that a disk would have h-bar of 0.1?
Yeah, like.
It's really unrealistic for massive black hole binary disks. I mean, since they are thought to be very similar to AGN disk, they would have aspect ratio below 0.03. So I don't think we really need to be.
Yeah.
But again, this is just assuming isothermal equation of state. So like no like Shakur and Sunyaev solution where the aspect ratio is related to the m dot.
Now,
So
I was asking more in terms of, you said h by r equal to 0.1 is a sweet spot.
Yeah.
I was asking how much it depends on the other like.
Right. No. So yeah, this is an important thing that I didn't mention. All the simulations are scale free. So the binary mass is 1 and the semi major axis is 1, but you can take it whatever you want to be. Okay, so now all these previous simulations were just pure hydro, no self-gravity. The disk was locally isothermal. So neglecting self-gravity means that we neglected the gas gravitational force. So the gas didn't feel itself in previous simulations. So what we did was to ask ourselves whether this is a good approximation and in which region of the parameter space is this a good approximation. So we compared the self-gravity radius with the gravitational wave coalescence timescale, extracting essentially these two diagrams that show the mass of the black hole binary versus separation, let's say. And essentially what this means is that in this region, so for masses, let's say below 5 times 10 to the 7 and separations very, very small, it's fine that you ignore self-gravity. In this region, you are completely dominated by gravitational wave emission, so you don't really care. And in all these regions, actually, it is really important to include self-gravity because assuming just the locally isothermal equation of state and the self-gravity is negligible is not a terribly good approximation. So what we did was to include self-gravity in our code. We actually used a different one than before. This is Phantom, which is still an SPH code. It's a pure SPH code. This is again live binary surrounded by a self-gravitating accretion disk. Basically, the equation of state is adiabatic, so the disk is allowed to heat and cool. The heating is provided by PDV work, so compression. So when shocks occur, the gas heats. And then the cooling is modeled as a very, very simple Gammy cooling. So it's like the cooling time is supposed to be a constant times the dynamical time scale, which is a very, very rough approximation, but this is what we had at the moment. And so basically I'll just move forward to let you see just the spiral. So after a while, the disk forms spiral, which are gravitational instabilities. And these are the source of angular momentum transport outwards. So instead of having an alpha viscosity like all previous simulation, we here have gravitational instabilities that transport the angular momentum. We explored the temperature effect here. And basically we found that even starting with different aspect ratio, as you can see from the 3 snapshots on top of the slide, the binary shrinks regardless of the aspect ratio. And this is because so basically gravitational instabilities allow the disk to self-regulate into a state where the heating and cooling are completely balanced. And this occurs for aspect ratio in this range, which is perfectly consistent with the range where people find that the binary semi-major axis just decreases with time. And we also explored the effect of the disk mass, since the mass of the disk is important in driving this self-regulation process, because basically the disk self-regulates at an aspect ratio which is almost comparable to the mass of the disk. So that when the two are comparable, the disk is stable against gravitational instabilities. And yeah, we can just see that the more massive disk drive the binary to evolve on a faster at a faster pace, but that's to be expected, let's say. And also massive disk evolve drive the binary eccentricity, which is shown in the middle panel, to increase more significantly. We also, since the location of the resonances depends on the mass ratio of the binary knots in its eccentricity, we explored a little bit the eccentricity and the mass ratio parameters in these simulations with the student. This is an unpublished work and it's very preliminary, but this is just to show you that since eccentric binaries have been found also to expand, we always find binary shrinking in these simulations. And more importantly, the eccentricity will basically saturates about around 0.5 regardless of its initial values and regardless of the initial binary mass ratio.
This is still with self-gravity.
This is still with self-gravity, yes. These are the same as previous simulations, but just exploring more the parameter space. Okay, so far we've been focusing only on the effect of gas onto the binary black hole. But what we did was also to include in an analytical model, so we didn't run any simulation yet. We included also the effect that stars have and the gravitational wave contribution. So we assume the stellar hardening, which is the standard one, and the gas-driven expansion this time, because we wanted to see, okay, let's say that the binary expands as a result of the gases interaction. But stars drive it to shrink and gravitational wave drive it to shrink as well. So I wanted to understand which regions of the parameter space are really dramatic, if binary expansion, of course, if any. So these plots, well, they all show the upper panels show A dot, the lower panel show the residence time, which is essentially a like it's essentially A over A dot. And you can see the different contribution of stars, gas, gravitational wave, and the total A dot, which is the sum of these three components. And you can see that, I mean, this is for an Eddington ratio of 1. So the binary is assumed to be accreted at Eddington. And this is for Eddington ratio 0.1. And you can see that the gas plays a role, which is the red line, plays a role only if the binary is accreting, at least at Eddington. If below that, the gas is always below the stellar hardening, which is in blue, and the gravitational wave hardening, which is in green. So we really need to be, so this already now narrows down the region of the parameter space. So the binary needs to be accreting at least at Eddington. Now, there are two ways that you can explore the effect of gas in this picture. One, assuming that you fix the mass accretion rate, and one, assuming that you fix the Eddington fraction. If you fix the mass accretion rate, then the binary mass would increase like with the accretion rate. But then if you fix the Eddington fraction, then the accretion rate increases as the mass increases. So there are two different regimes. Yes.
I mean, the Newton's approximation. So this is, again, it's not including self-gravity. Right?
Yes. No, it's
a reservoir of 100.
Yes, it's to the, yes.
So it could be that the gas in reality has a stronger effect once, because you show that the self-gravity.
That's true. Yeah. No, this is just a very simple analytical prescription that Munoz has, but yeah, I mean, it has to be investigated in further details for sure. I'm not sure we can recover that with our simulation. I don't think so, but anyway. Okay, so now this is the result that we obtain by fixing m dot. So you can see here the m dot values that we took. So 0, 10 to the minus 4 solar masses per year, 10 to the minus 2, and 0.2. We started with a binary with 10 to the 4 solar masses, we assume equal mass binaries just as a simplification, because if the binary has an unequal mass ratio, then it will quickly grow towards equal mass. And so basically, probably the more understandable panel is this one. And so basically you start at 0.1 parsec. And then if you accrete very low mass, then you will just go down, so you will just shrink. Also at 10 to the minus 2, it just shrinks. While if you go up to 0.2 solar masses per year, then at this point, it just hits the point where the gas starts to dominate. And so you have a slight expansion along, this is the self-gravitating radius. So the binary will expand this way, and then it will hit basically since it accretes mass, so its mass is increasing, it will hit the self-gravitating regime and then go back to shrinking, just because as I showed you, in the self-gravity regime, the binary is expected to shrink. This is the same exercise, but fixing the Eddington ratio. So you can see here the number, it's 0.61 and 3. And you can see that up to, as I said before, Eddington of 1, you just have binary shrinking, no questions about that. In the case where the binary is accreting at Eddington or super Eddington, then you can have a binary expansion. Again, the binary mass grows and it hits again the self-gravitating radius, then going back towards shrinking.
So
yes.
In the last slide, the 0.2 solar mass per
yes.
0.2 solar mass per year for a 10⁴ solar mass black hole. Isn't it too high accretion rate? Is it?
It is very high.
There's like 10,000.
Yes. We had to push it to see expansion. Yeah. Okay, so this is here we changed the initial mass by keeping the Eddington fraction fixed, and basically you can see that again all these curves undergo the binary expansion phase, just because the Eddington fraction is 1, and so the binary is accreting a lot of gas. But then, like if you start with 10 to the 7 solar masses, then you will hit the gravitational wave-driven regime way faster than the expansion. So for masses above the 10 to the 7, then the binary will just shrink. Before, because of stellar hardening, and then it will just go directly into the gravitational wave-driven part of the diagram. So. And so what we did at the end of this work was just to compute the coalescence time for all these cases. And as you can see from this is very crowded plots, but you can see that essentially we never have a coalescence time which is longer than the Hubble time. So this means that regardless of possible gas-driven expansion, in our picture, where we assume that after the binary hits the self-gravity regime, it will just go down. And we just have a very simple analytical prescription for the evolution of the binaries in the major axis. Basically, the coalescence time is always shorter than the Hubble time for all the scenarios that we explore. So all the different initial masses, fixing m dot or fixing the Eddington ratio, and basically that's it, yes. So in summary, I would say that the binary semi-major axis decreases with time as a result of the interaction with the gas in a vast region of the parameter space. And since we expect the circumbinaries to be quite cold, we don't have to worry about expansion because the gas will always remove angular momentum. We resolve binary shrinking using this hyper Lagrangian refinement with the particle splitting, neglecting the discrete self-gravity. So that's one of our next steps. And in the self-gravity regime, we've seen that regardless of the initial parameter of disk, such as mass and h over r, the binary just shrinks as a result of this interaction. If the disk is very massive, then it will drive significant binary eccentricity. And finally, even if we consider the very worst case scenario where the gas drives the binary expansion, but there are stars and gravitational waves as well in the picture, then the binary will still manage to reach coalescence within a Hubble time. And this is all. Thank you all for the attention. I'll take any questions.
So we have time for many questions to start.
So the movie was very good enlightening of the binary and driving of the gravitational turbulences into this. And it seems like that this is kind of a steady process, right? So I wonder, so if you had the special case where you had the third black hole come in, that would essentially really destroy this periodicity, right? I would imagine. And so is it possible that in this case you could drive even stronger spiral features and lead to a...
I would guess that that's really possible. It will depend on its mass and inclination with respect to the disk. But yeah, for sure. I mean, even flybys will just alter this. And this, again, the formation of these spirals, it seems to be really a result of the cooling prescription that you use. So if you change the cooling prescription, or I mean, if you consider a third body that will hit the disk, it will probably heat up the disk as well. So yeah, definitely that will alter the picture for sure. Yeah.
Yeah. So it might be an easy question, but when I saw all of your descriptions for the book for the accretion disk, sorry, I saw all the alpha parameters, fixed aspect ratios. Could you maybe explain again, how do we model this? Is this all analytic modeling of the disk? And,
you mean in this last work that I was talking about?
Yeah, like
this one.
You often said, oh, alpha, fixed alpha to be.
Oh, okay.
This, right? But then I wonder, I mean, it's a good analytical approach, I suppose, but like, could a more evolved treatment of all of those of the disk basically change the results?
Yes, definitely. So well, alpha disks are a very simplistic modelization of a disk. So alpha basically encapsulate the effect of, let's say, MRI or gravitational instabilities. All processes that are very different to include to get an analytic prescription. So it's not, you should really resolve the MRI to understand viscosity in accretion disks. So yeah, to answer your question, then yes, it is a simple approximation. I think that already assuming a much more realistic cooling will alter this picture, and I'm sure assuming MRI-driven viscosity will alter this picture as well, because the results are very sensitive to the disk viscosity. Yeah.
This is basically not the first priority.
No, not really, no.
I think it's to follow up the question. In the case where you included gravity, right? That as you said, you have basically included a physical model for
angular, yes.
Maybe you looked at that, you could measure an effective alpha and compare it with
yes.
what you normally use, and if it's larger, then it's just dominant. You don't worry about the MRI.
That's correct. So from the self-gravity disks, you can measure an equivalent alpha. You have to assume that the disk is in perfect equilibrium. And also you can, I mean, there is a simple analytic prescription for it, but just for beta cooling, which is a very, very crude approximation. Lawrence?
I have a question. I think about the slide before where you showed the final mass here.
Okay.
So you showed us the cases where you have 0 accretion, 0.6 Eddington, and 1 Eddington.
Ah, sorry, the slide, this one. Okay.
And
yes.
I would think that most black holes are somewhere between 0 and 1, let's say most AGNs at least at redshift 2. But it seems that actually the final mass of the binary, it's actually very, very sensitive on that F Eddington, where you end up when you're all the way to the left.
Yes, because if you fix F Eddington, then the n dot increases with the mass.
Yeah. But
so as the binary accretes, it accretes more. Like as the binary becomes more massive, it accretes more.
I don't know what is more reasonable to fix F Eddington or the accretion, but I wonder if there's, I'm wondering if this sort of, let's say if you give it an input, like a mass distribution of all galaxy mergers and the black holes that merge, and you sort of plot this, and then you get a mass of all the binaries that you will get at the end. Yeah. Would it change a lot what Lisa, for example, is expected to see, like bias towards higher masses, or is there a way to plot, you know, an initial mass distribution, put it through this method, and get out a mass distribution for Lisa?
That can definitely be done because this is a simple analytical model, so we don't have simulations or anything, and it's based on very simple assumptions. So I think, yeah, I think that can be done. Yes, that's interesting actually.
If you really bias everything towards either the top,
yes,
the top of that line that seems quite consistent.
Yes.
Yeah, just how I thought.
Yeah, no, that's interesting. Thanks. Yeah.
I have a question about the last conclusion point that these things emerge in Hubble time. And I think the time scale looks to be around 100 million years. But I think the big question, I'm just trying to get your thoughts, how to get them to 1 parsec and the time scale to get to that stage. Do you have any idea of that final time scale? Because that's a more important time scale. Like once we get to 1 parsec, then it merges in 100 million years, as you were saying.
Yeah.
But before that,
that's true. Yeah. Yes. Yeah, I don't know. I mean, up to 1 parsec, well, let's say at 1 parsec, the gas contribution is negligible. So you have stars and dynamical friction. So stars are quite efficient hardening drivers. But I'm not sure, I might be wrong about this, but it seems that dynamical friction is not giving the right answer either recently. So there is still some debate, I think at like kiloparsec scales, if I'm not.
The issue is also, you know, the 10 to 100 parsec scale is the critical one.
Yes.
Because actually gas their main matter significant, as you said, you know, that you can have spiral density waves on this scale that actually dominate over the stellar driven dynamical friction. So it's another unsolved problem. Maybe it becomes more worrisome than the small subparsec scale.
Yes, of course. If the binary doesn't get to 1 parsec, then it's done. Yeah.
I had one on the aspect ratio, because you mentioned that the aspect ratio is important in many things, is the thermodynamics, basically.
Yes.
And you said the typical agent is single black hole. The ones that we study, you know, observation, that they are supposed to be thinking of the thermal structure. But when you have the cell gravity included, I can imagine that you have an effect on the aspect ratio as well, because usually we include the waves that propagate also vertically.
Yes, that's good.
How much does that evolve, the H over I mean, once you start with a given value?
Yes.
Does it become significantly larger, or does it?
No, it actually cools down.
Okay.
So this is starting with like regardless of the value you start with. So even if you start at 0.1 with a 0.1 mass disk, then the disk will self-regulate in this region of the parameter space.
So that's a self-regulated parameter.
Yes, exactly. If you take much lower mass disks, then it would be even lower, because essentially, so the stability of the disk is regulated by the Q parameters, right? So this is the temperature divided by the mass. And so if this Q is of the order of 1, then you have the instabilities. Above you're stable, below you fragment. And so yeah, I mean, it depends on the mass of the disk, but then again, I mean, even 0.1 is a very high mass disk. So you would really have to be, I don't know, if you take probably h of r of 0.1 with a disk mass of 0.5, then maybe you, you either fragment or you push h over r a bit higher.
Yeah, that's what. So it's really so changing the beta.
Yeah, no, yeah, definitely. I mean, we are running simulations with like a black body cooling, which is slightly more realistic than this one, and the picture is quite different. So I mean, as you've seen in this simulation, for instance, the cavity stays perfectly circular. It doesn't develop any lump, anything. But I think that's a very clear indication, like a very clear feature that is given by the assumption of the cooling. But yeah, even in this case, we are trying to measure the equivalent beta to compare. Yeah.
So would you say, or at scales of like 10 to the minus 2 parsecs, if you have, I think you would expect that for every 1,000 orbits or something like that, if you have an eccentric binary, you actually process one full roundabout because of relativistic modifications. And I wonder if it would be hard to put in a processing binary in, for example, a simulation with a fixed orbit. And if you think this would change some of these resonances, and if it would have an effect on all this Lindblad resonance theory, because I don't think, for example, post-Newtonian effects are considered, you know, these resonances and things like that.
No, I don't think so. It's all Newtonian. Yes, that's right. Yeah, I'm not aware of any work that did that particularly. But yes, I mean, it might change the location, and probably, well, the strength depends on how much material is there. Yeah. So,
are you able to follow several thousands of orbits?
Yes. Okay. Yeah. I mean, it's expensive.
Yeah.
But yes, 2D is much cheaper.
So no more questions. Thank you.
Thank you.